Hi everyone, my name is Tanner Reece, and I am a graduate student at Washington University School of Medicine in St. Louis. And for my repro rehab project this year, I wanted to write a script in R that will perform non-parametric bootstrapping on mixed effects models. So if you're unfamiliar with either mixed effects models, bootstrapping, or both, I would highly encourage you to read a little bit more about each of those methods before trying to apply those methods or any method kind of covered in this script in your own research, but hopefully we'll go over the basics here. So to start, I've already done some of this for the purposes of demonstration, but we'll load in the relevant libraries, clear out the environment that was um, any objects or any um, data structures that were in the environment previously, and we'll clear those out, update the working directory, and then we'll load in the data. And so the data for this example come to us from some recent work in our lab where we obtained uh, outcome measures on motor units measured in control subjects and participants with MS. So in the subject ID column, you'll see MS01 repeated, I think probably a few hundred times or close to 100 times. The reason why is because each observation here represents an individual motor unit we observed for MS01. And similarly with MS02, each row here corresponds to a motor unit that we observed from the subject. And the idea behind mixed effects modeling is to sort of detangle the subject level, the between subject variance, from the between motor unit variance to better address the research questions that we're interested in while taking into account the hierarchical or the nested structure of our design. Um, and so these first few lines here are running some of the resampling functions that will be called during the bootstrapping code. And for those that are unfamiliar or maybe have a loose familiarity with like what bootstrapping is, the basic premise is that when we run a standard linear model or a mixed effects model, that comes with certain assumptions about the sampling distribution of those coefficients that we're interested in. And when things like homogeneity of variance, normality of residuals, when those sorts of assumptions are called into question or they aren't met, especially to like a large degree, the inferences we can make about those coefficients, the inferences that we make that go to inform kind of our hypotheses and our research questions, can be called into question. So what the idea with bootstrapping then is that if we assume that the sample we've obtained is representative of the population we're interested in, then as a stand-in for random sampling from the population, we can just sample with replacement from our original sample. And that the validity of that is strengthened with things like random sampling and then like just increased sample size and things along those lines. But as long as that assumption is reasonably valid, then bootstrapping provides a great alternative to make some defensible inferences about the coefficients and the questions we're interested in. So I talked about resampling, and I'll talk a little bit more about what that is because it's a little more nuanced when it comes to mixed effects designs or mixed effects models. And so to start, this function here entitled level 2 resample, I actually pulled from, I modified it a little bit, but I pulled largely from Tristan or TJ Mars website, and that is linked here. But the idea here is, if we have um, our original data here, what level 2 resampling does, well, let me back up a little bit and distinguish between level 2 and level 1 in our data. So I mentioned that these data are nested and that we have multiple motor units within each subject. So level 1 is going to refer to our lowest level of observation, which in this case is the level of the motor unit. And then level 2 refers to the level of the subject. So when I talk about resampling with replacement, we can do that either at level 2, at level 1, or at both level 2 and level 1. So to start, level 2 basically just consists of taking a random subject from this data frame, pulling out all of its data. So if we randomly drew MSO1, we would take observation 1 here all the way down to observation 83, take all of its data, put it in our bootstrapped data set, our resampled data set, and then we would put MSO1 back in the original data set such that it has, an equal probability of being sampled each time. And I'll kind of show you what this means in a second, or how this looks in practice when you perform this level 2 resampling, but that's the gist of it. So we're resampling at the subject level with replacement. So with replacement, meaning that, after we sample MSO1, it's entirely possible that we could sample MSO1 again. And each time we sample at level 2, all of their motor units are coming with us, or coming with that subject. And then when we talk about level 1 resampling, on the, as another alternative, what we can do is leave all of the subject IDs alone. So all of the subjects are going to be all of the same subjects are going to be present in our resampled data set. But within each subject, we're going to resample with replacement from the motor units. So essentially, for however many motor units or observations MSO1 here has, what did I say, 83, we're basically going to pull with replace or sample with replacement from MSO1's motor unit. So this first motor unit, let's say we sample it randomly to start, has a DF value, which stands for delta F, of 1.18. And so we could sample it, put it in for MSO1, put it back in the original sample, such that it has an equal probability of being sampled again. So essentially the same idea. You could have multiple motor units or duplicate motor units for each subject with level 1 resampling. And then the most conservative option, and the option I default to typically, is just performing both. So performing level 2 resampling, and then also performing level 1 resampling. So I'll show you what each of those look like if you're having a little bit of trouble kind of wrapping your head around each of those examples. So to start, I'll just run these functions. And then this level 2 resample function takes in as arguments the data frame, the number of level 2 units we have. So in this case, just the number of unique subjects. And then this ... syntax in R just basically allows us to put in other arguments that might be specified or that might be needed in the function. So in this case, we'll put here the grouping variable that we have. So basically the subject ID column. So just SUBJID. So if we do level 2 resample, data level 2 units equals subject ID count, and then subject ID, this is just the name of that column. And then we'll do view. Yeah, so you can see the first subject sampled here was ankle 17. And we could scroll through this list. It has a similar number of entries, so it's hard to digest just by scrolling. But for reference, what we can do is look at data, subject ID unique length. So this is the number of unique subjects we have in our original data frame, should be 50. But if we do that level 2 resample, instead of view, I'm just going to do whole subject ID unique length. We see, because we're enabling the function to take the same subject multiple times, we now only have 30 unique observations, or 30 unique subject IDs. So that's level 2 resampling. So the idea is you sample at the subject level, and it is, just keep in mind, it is possible or it is expected that you'll have multiple some subjects in there several times. So you won't have the original number of unique subject identifiers. So level 2 resampling, or level 1 resampling, excuse me, is a little simpler. We'll just do level 1 resample. And I think this just takes in the data. So if I just input the original data, we'll do view. So it's the same number of observations as the original data, but as you can see, trying to find an example. The point is, it's possible to have duplicate observations within a subject because we're resampling with replacement at level 1. So if we do that same exercise looking at the unique the number of unique subjects at level 1, we see even after we replaced or resampled with replacement at level 1, we still retain the initial 50 unique subject identifiers. And then to basically perform both level 2 and level 1 resampling for each bootstrapped iteration, this compose function basically just combines those two into one function. So I cleverly titled it level 2 and 1 resample. So that's all this does. That tends to be the most conservative approach. Typically, I would lean on performing both. The exception to that might be if you have like some longitudinal data, where that level 1 covariance variant structure might be something you want to retain, so that like observations closer together in time are going to have a structural, like a correlational relationship that's going to be accounted for in the model. And when you resample, things like that might be compromised. But in general, I would err on the side of just resampling both. This model function, I think, is just something I had written to incorporate into later functions just to help clean up the code a little bit. But all this does is just takes the data and then a model formula and performs a mixed effects model using LMER. Okay, so the idea behind this code is that it takes in a model, forms the bootstrapping, and it then on all the bootstrapped iterations. So we have basically that empirical sampling distribution. So we build up from each bootstrapped iteration, we pull out the coefficient of the model that we calculate. And from that, we get an actual distribution of what that coefficient's sampling distribution looks like. And so in this case, what we're going to do is resample that model, or resample the data, perform a mixed effects model. And then for like an initial significance test, what I'm telling this function to do is calculate the ANOVA, or using the ANOVA package, basically the F value associated with each term in the model. So that's what this is going to do. And then you'll see this in a few lines. But after we determine which terms in the model are statistically significant by looking at that F value from the ANOVA test, it basically then goes in and automatically performs the appropriate post hoc tests using estimated marginal means, or this e-means package, which if you haven't seen, you will later in the code, but it effectively just performs like post hoc comparisons if we have factorial main effects, or if like factorial interactions in our design or in our model. So that's what this does. Next, we have em means specs function. So specs, I think, is short for specifications, and the only reason I called it that was I think that's just the name of one of the arguments in the e-means function we'll use. But essentially, it's just a function here that takes into account a significant table of the terms from the bootstrapped ANOVA, and then it just basically determines, okay, what factorial main effects or what factorial interactions do I need to perform post hoc tests on. And I'll talk a little bit more about this when we actually step through an example, and this will make more sense. Okay, so now that all those functions are out of the way, this is what actually performs the bootstrapping. So to start, in this case, it's often the case that we have like a handful of motor unit variables that we're modeling as outcomes, and we're interested in a very similar model formula, applying a similar set of fixed effects and random effects to multiple outcomes within our data set. So this just basically enables us to perform these bootstrapping analyses on multiple models in bulk. But for purposes of demonstration today, I'll just step through one of these models. So here is a brief review of this LMER or LME4 syntax. So similar to just the standard LM function in R, it takes your outcome on the left of this tilde, and then all your fixed effect terms, and then you can add another term for the random effects here. And again, this isn't supposed to be a like a full-fledged review on mixed effects modeling. There's plenty of great resources on the internet for that. So if you're confused about sort of what a random effect or a fixed effect is, I would encourage you to look into that. But here we're just specifying the formula for fixed effects as a string. So for this example, we were interested in looking at the three-way group by muscle by recruitment torque interaction, and then also accounting for age and sex as covariates. And then the random effects formula here, we're basically saying we have multiple observations nested within subject. But one thing I didn't talk about here in this data set, we also have multiple trials within subject. So for MSO1, we have trial 101, 111, and then 131, for instance. And what this is capturing is saying not only are there dependencies of those motor units within a subject, motor units within a given subject tend to be more similar than motor units from different subjects. But motor units within subjects within a given trial are still going to be more similar to each other, even still. And this basically just adds a partition to the variability that accounts for that. And then lastly, I don't think I mentioned this either, we also have two different muscles that we record motor units from for each subject. So we have the TA and the soleus. So basically just accounting for the different levels of nesting of those motor units within the data. So now that we talked a little bit about specification of the fixed effects and the random effects formulas here, what we can do is run line 162 here, and what that we'll do is actually go in, and for each of those outcome measures, those DVs in our list, it will run a mixed effects model using LME4 with the specified fixed and random effects structures or specifications that we've defined up here. And as you run those, I notice, and you'll almost certainly notice this in your own work, occasionally when running these models, you'll get these singularity issues. And what that is getting at is that the variance that is accounted for by any one of these random effects is virtually zero or very close to it. There are some other things that could mean, but in the context of the particular type of model we're working with, where we don't have any correlated random effects or anything like that, we just have these what are known as random intercepts for subject by trial, and subject by muscle. The singularity is just getting across that one of these intercepts is capturing no variance. So that's what that singularity warning is telling us. But within, so we get those warnings as we run this code. But what this if else statement down here does is if it detects that a model run is singular, has a singularity warning, it'll actually go in and using some extractor functions, this var_core function actually looks at variance of those random effects. I can use that real quick. So just running, yeah, so it's just looking at, so we have subject by trial intercept, subject by muscle intercept, and subject intercept, just like we defined. And it wasn't, the singularity warning was not for this particular model, but if it were, you would see a standard deviation for one of these of, excuse me, 0 or a very low number. But what it does is if it is singular, if one of these is 0, it'll go in and basically rerun the model without that random effects. So we get a singularity warning initially, but the model that's actually used for bootstrapping does not have a singularity warning when it's the formula does not have a singularity warning on the original data when we perform the bootstrapping. So we have our list of models, and now we can actually get into the bootstrap code. So what these first few lines do on 223 to 225 are just basically set up our system for parallel processing. So we're detecting the number of cores on our machine. I think in mine it's like 8 or something. Yeah, so it's just 8. And the plan is to perform parallel processing using this multi-session function. And for the number of workers, it's sort of common to specify the number of cores on your machine -1. You want to leave one processor free to run other sort of routine operations of your computer. So we'll do that. Okay, so the number of resamples you'll want to perform for bootstrapping is kind of going to depend, I guess, on your discipline, but you want a sufficiently high number of these such that you actually get like a good estimation for what your sampling distribution is. So the minimum that I've sort of heard and seen and talking to people that do this sort of thing routinely is 10,000. But with mixed effects models specifically, you'll get those singularity warnings. You'll get non-convergence issues. You'll get warnings with some of the bootstrapped iterations that make any statistics, any F values, coefficients we could extract from it invalid or at least questionable. So because we're going to basically account for the fact that we're going to lose some of our bootstrap samples, I like to bump that number up to at least 15,000 and in some cases 20,000. Just because it still runs in like a reasonable amount of time. So it's not too much more cumbersome. But for now, just for example purposes, we'll set that at 10, just stupidly low, just to get a feel for what the code is doing. Okay, and then at 232, I think the rest of this, yeah, so the rest of this is all just basically one big map function that loops over our list of models and performs the bootstrap procedure on them. But for just demonstration purposes, what I can do is just kind of work through the contents of this function directly. And I'll do that just working with one of these models. So basically this first line here where we define the model formula, I'll just set that equal to the first element of our models list, which I think was like the model for that df variable. So do mod formula. Yeah, okay, cool. And so the first step is this argument here termed model results. So if I run this, what it's going to do is perform level 2 and 1 resampling on the data, run a mixed effects model using the formula we specified, and then basically use the ANOVA function on that mixed effects model to obtain the F values for each term to determine statistical significance. And these wrapper functions on the outside here, these safely and quietly functions, those are our error handling functions. So those both come from the purr package. I might mix up which one is which, but I believe the quietly one is to suppress warnings. So you'll see as we ran that, we didn't get any warning output here in our console, because what it does is it basically puts each warning that may have popped out or almost certainly popped out at least once in a separate item in a list. And I'll show you that in a second. And then safely, I think, is a similar idea, but it's specific to errors. So if we get like an error, it'll put that in a different list as well. So the idea is we're going to catch those errors, those warnings, those things we want to flag, but we're going to do so without stopping the code. So if we look at model results, it's a list with the number of items that match to the number of iterations we have. And those safely and possible or quietly functions basically create like the sort of nested list structure, which is a little annoying to deal with at first, but you kind of get the hang of it by playing with it a little bit. So this is the safely. So here we did not get any sort of error, so we just have our result. But because we use that quietly function too, we have another nested layer in our list that has any warnings or outputs or like side effects from running the code within that quietly function. So in this case, we didn't have any issues, so we can just look at the result, and it's basically just the f values for each term in our bootstrapped model. So this isn't list form. I think the next line kind of cleans it up a little bit to make it more digestible. So this filtered model results, this just basically loops through using this keep, which is sort of like a map function. It's again from that per package. I encourage you to read the documentation because it's pretty useful, but it just looks through that model results list and only keeps the results that don't have any warnings or error messages. So if I look at that, then here we are. So here we get basically a concatenated data frame that has the 9 terms for each model. So we should have 9 terms times 10 iterations. Yep, 90 entries. So for each of those bootstrapped iterations, we ran, resampled, ran a model, used that ANOVA command to get the f values, and we get those f values for each term that we have. So group through that group by muscle by torque recruitment interaction, and then it starts over. So, and then this bootstrap samples ANOVA. All that does is it just saves basically the size of that list that we have that don't have any errors or messages. So this is just a way of tabulating. We wanted 10 iterations. Did we actually get 10 iterations? As you get into the thousands, you'll see, you might want 10,000 iterations, but the actual length, once you take out any bootstrapped iterations without any warnings or messages or errors or whatever, it might be, be like 9,000 and some change. But that's all that's tabulating here. And then these 2 lines actually sort of tabulate our results for us. So we get this basically extracts out the unique terms in our filtered model results and basically calculates the bootstrapped confidence intervals for those f values and puts them in a nice table. So for each of those 9 terms, we get the mean of those 10 bootstrapped f values, and then the lower and upper 95% confidence limits. Now, again, there's a lot of literature on exactly how to go about calculating those confidence intervals, but my understanding is I think the most supported method is this BCA, which stands for bias corrected and accelerated, I believe. Yeah. And it's just, I think, a way to get more defensible confidence intervals for those bootstrap values. And then, so we get, the lower and upper boundaries of those confidence intervals, assessing whether or not it's significant at that alpha equals 0.05 level. And in this case, our null value, the value we don't want in our confidence interval is not 0, because an f value cannot be 0. It's 1. So a f value of 1, if you remember back from undergrad or graduate stats or whatever, just signifies that the variance accounted for by the regression is not any greater than the error variance, essentially. So Yeah, so we see like, for instance, this three-way interaction is not significant. However, the two-way group by torque and muscle by torque interactions are significant, along with the effects of age, recruitment torque, and muscle. And then it just outputs the dependent variable here as well as another column. All right, so we have kind of our primary results, but for instance, with this group by torque interaction, it might be useful for us to like do like some sort of post hoc testing and look at actually what that mean difference is, when we adjust for torque or recruitment. So for that, what we can do is basically this just pulls out those continuous covariates and just tabulates the factors separately. So any term that just has a factor in there. So muscle by torque recruitment group and then muscle. And then it just basically pulls out or it runs that specification function to pull out the terms we want to perform post hoc testing on. So when we run that and store it in specs, the function I wrote basically looks for the highest order terms first. So in this case, because we have a muscle by torque at recruitment interaction, we want to definitely analyze that, but it wouldn't make a whole lot of sense, or it wouldn't be all that interpretable then to look at the muscle main effect because it varies as a function of torque. So with that being the case, the function I wrote, that EM specs function, basically just pulls out the highest order terms, and it doesn't look at the lower order terms if they are involved in these higher order interactions. And then, yeah, so if there are no significant factors like that we need to perform post hoc tests on, I think I just set it to return where is it? Yeah. So in the else case, it just indicates that there are no significant factors. But assuming there are, like there are in this case, this EMM result, we can run. Oh, whoops, hold on. Didn't finish the function. So basically, we use the ANOVA to inform significant interaction terms, what have you. And then what it does next is it basically performs the e-means that we want to perform post hoc testing on. So it performs new models. Basically, it runs that resample model and then extracts the e-means from it. Given our the specifications that we want. So let's run this function and you'll get a better idea. So result, again, I use that safely and quietly kind of pair. So if we look at the significant e-means, we get yeah, so we get like a data frame that indicates what group we're looking at. So this is looking at that group. Yeah, this is looking at that group and muscle group by torque and muscle by torque interaction. So we have the group here, control. If we look, the estimated marginal mean for the control group at mean recruitment torque is 3.5. And then for the MS group, it's 3.17. And then that control minus MS contrast, so that pairwise difference, is going to be 0.3 or 0.33. And then similarly, these last rows 4, 5, and 6 aren't looking at the group by torque interaction, but the other interaction we found significant. So that group, or that, excuse me, that muscle by torque at recruitment. So for the soleus, at the mean recruitment torque, it was 2. The delta F value estimated marginal mean was 2.4, and then 4.2 for the TA. And then that soleus minus TA contrast was negative 1.7. So that's all that does. And then similarly, it goes through and filters if we have any issues like warnings or singularity issues or anything like that that are associated with those models. Um, it will throw those terms out and filtering them. And then it'll also keep the length or the number of actual models that we retained after throwing out the ones with warnings. That's about it. Oh, it also, yeah. So finally, it puts it in the significance table similar to the ANOVA one. So if we look at here, we get both the estimated marginal means and the contrasts in one table. So this is just the control group at the mean torque of recruitment, the 95% confidence intervals as well as the mean. We see it's significant. So we see like both the marginal means for each group here, and then that contrast is also significant. And then now looking at the muscle by torque interaction, we see both marginal means are significant as well as that contrast. And then I think that's about it. These last few, this last chunk is largely duplicated. If you ever wanted to look at estimated marginal means that maybe weren't significant from the ANOVA, just for like exploratory purposes, this just allows you to do that too. So in our case, regardless of what the ANOVA said, we always wanted to look at the group by muscle cell means just to see what they were. So that's what this does. But then lastly, so you'll run this code, and then the last thing it will do is basically create a folder for you with the date, and it'll save both the ANOVA, the significant e-means table, the original data file. Does that? Yeah, it saves the original data in that folder just for your reference, as well as an RDS object. So basically it just saves the raw bootstrapping results. So I think with 10 iterations, it won't take that long to run. So I could probably just show you what it does real quick. So this is, I was stepping through an example where we just had one model, but if you did want to run multiple models in succession, this is what would, okay, so the bootstrap code finished running, and what the results are, what's saved, or what's saved to this bootstrap results object is essentially a list for each outcome name in your dependent variable list. Then if we click here, we get that ANOVA table that we've seen before. Yeah, that ANOVA table that we've seen before for each model term. We get the significant e-means object, which is basically the estimated marginal means and the appropriate contrasts for the significant factorial effects as defined from the ANOVA output. And then here, regardless of what the ANOVA output indicated was significant or not, this was just an extra layer we added just to obtain the group and muscle marginal means and contrasts. And then, so that's the bootstrap results. And then when you run it, it also saves all of those guys. Here we go. In a new folder with the date. So I've just been writing univariate bootstrapping results. So bootstrap results, then it appends today's date on there. And then we get separate folders for the ANOVA, the group mean, or the group muscle, estimated marginal means, the significant estimated marginal means. So all those CSVs are in there. And then the original data file as well, just for your reference. So that's it. It's far from perfect, and I'm still kind of continuing to polish it to meet the needs of the lab and the needs of the specific research project we're working on. But I hope you can use this in your own work for your own mixed effects models, or at least parts of this script can help you in some way. If you have any questions, feel free to reach out and contact me. Or if you have any advice, I'm still um, learning about the functionality of a lot of the packages and things I used in this script. So if you have any advice or tips or tricks or on how to make this code cleaner or more efficient, I'd be more than happy to chat about them with you. So thanks.